Hi, this is Phil Koopman, and I'll be talking about key ideas for UL 4600, which is a safety standard for autonomous vehicles. Let me start with an overview. The UL 4600 standard covers autonomous vehicle safety cases. That includes fully autonomous vehicles without a human driver. It was issued in April 2020. Here are some key ideas for 4600. First, a system-level safety case provides direction. Next, the vehicle as well as infrastructure and lifecycle processes all matter and have to be included in the safety case. Safety metrics are used for feedback loops to help continuously improve even after deployment. Third-party component interfaces protect proprietary information for third-party component vendors. Finally, conformance to 4600 helps you know that you've done enough work on safety to be able to deploy in a responsible way. 4600 uses a goal-based approach to do safety. Traditional safety standards such as ISO 26262 and others are more prescriptive. They say, here's how to do safety, and they give you a process or process elements you're required to perform, and they tell you which work products you're supposed to produce. Those standards are not displaced by 4600. 4600's approach is to add another layer of completeness, so it's goal-based. What it says is, here's what a safety case should address, and that tells you what goes in the safety case and the types of activities you need to perform. It does not prescribe any particular engineering approach. As we'll see later, for example, it says, well, you have to have a list of all the hazards that matter, but you can use pretty much any reasonable way to get there. So that means this can work with other safety standards, and the work products from those other safety standards are incorporated into 4600 as part of the safety case. That makes 4600 a standard on how to assess a safety case. In other words, what the minimum coverage requirement is to have a complete enough safety case, although probably you want to do more depending on your system. The properties of a well-formed safety case, such as making sure that all the evidence traces up to goals and the other way around. And independent assessment criteria, so that an independent person can come in and know that your safety case is well-formed. Let's dive right in and take a look at a little piece of the 4600 standard. This is clause 12.3.1, which has to do with verification and validation of faults related just to the design phase. There are other clauses for other design phases. This one says, V&V shall provide acceptable coverage of safety-related faults associated with the design phase. So that means your safety case has to talk about faults related to the design and how you're going to verify and validate that they are not existent or that they've been mitigated in some way. Within each clause are a number of prompt elements organized by category. In this case, we're looking at the mandatory prompt elements for this clause. So every bullet item here is interpreted within the scope of the overlying clause. So that means A, 12.3.1.1a is for safety-related faults and for V&V related to the design phase, think about systematic design defects. It doesn't tell you what to do, it tells you your safety case has to have somehow addressed the topic of systematic design defects within that clause. Jumping down to E, it also means that there might be design defects having to do with the identification description of the intended ODD. In other words, your description of the ODD might be incorrect. All these are mandatory. That means they have to be addressed in your safety case. It does not mean you need a technical mitigation. It just means the safety case has to say risks and hazards introduced by these are mitigated either because they can't happen, or we have a technical measure, or we have a non-technical measure. Moving on, every clause also has a required section. These are almost mandatory. What that means is if they apply to your system, you have to cover them in your safety case, but there are some systems which they might not apply. So for example, 12.3.1.2a, maintenance procedure definitions, it's conceivable that a very simple system might not have any maintenance. It might be built and it might run until end of life with absolutely no maintenance whatsoever. If that's the case, you can say we're going to deviate from this prompt element A. In other words, we're not going to do it because there is no maintenance for our system, and that's okay. So you do not have to address prompt elements that don't apply to you, but you do have to write down if it's required, does not apply to me, here's why. 12.3.1.3 is highly recommended. In this case, there aren't any. It's a placeholder for future versions of the standard. Highly recommended are things that you really ought to seriously consider, but if you decide it doesn't apply to you, that's okay, and you might just say, well, we're not doing this because we have another way, or we have some non-trivial reasons why this doesn't make sense for us, and if that's true, you don't have to do it. Subsection 4 is recommended. Recommended are even less stringent. Recommended are just good ideas. You don't have to address them in your safety case, but they're there to document things that might be useful to some teams. Finally, every clause has a conformance section, which is how the assessor takes a look and checks conformance. In this case, inspection of design and V&V evidence. So the idea is that all the clauses have a conformance section, and the point of this standard is to be as concrete as possible in how to assess to make sure you conformed. The standard provides a lot of flexibility. Besides the ability to deviate from everything except the mandatory prompt elements, there are also lists of alternate approaches that can be used. For example, in 6.4.1, which talks about criticality levels and initial risks for each hazard, it requires that you have a hazard log. You have to write down a list of all the hazards you need to mitigate. But how you get there is entirely up to you. There are a number of techniques, risk tables and fault trees and event trees and bow tie diagrams and using STAMP, or number 10, other relevant risk evaluation approaches. You can do whatever makes sense, and you might do more than one of these. You might do some combination of these. It doesn't really matter as long as you did something, but what does matter, what is mandatory, is you have to have a written list of hazards in the end. So much of the standard allows considerable flexibility in the technical approach, but gives you examples of the types of things that you might want to do to be responsive to the standard. Now, all these clauses operate in the context of a safety case. You absolutely have to have a written safety case to conform to 4600. So what's a safety case? Well, a safety case in general has three parts. One is a claim or a goal, such as system avoids pedestrians. That would actually be a subset of all the claims, but it's an example. There's an argument why this is true. For example, we plan to detect and maneuver to avoid pedestrians. And some evidence. You can't just argue. You have to have some evidence behind the argument. The evidence might be tests, analysis, simulations, various things. So the idea is the entire safety case is a chain of claims at the top, arguments in the middle, and evidence down at the leaves. Now, a single claim with a bunch of flat arguments probably isn't going to work out. So manage complexity and break down the task of assuring safety. There are typically subclaims. For example, argument 2, if it has to do with avoiding pedestrians, might be we avoid pedestrians, but we do it by detecting them, and then we maneuver around the detected pedestrians, and then we stop if we can't maneuver. The scope of the safety case in 4600 is everything needed to independently assess safety. So that means the safety case should have everything in it that you need to decide that, yep, sure enough, this system is safe. That includes the hazards, the mitigation approaches, and all the arguments traced to evidence. The scope includes technology, hardware, software, machine learning, tool chains, data sources. It includes life cycle. It's not just deployment, it's also operation, it's incidents, it's maintenance, all the things in the life cycle. If you have a vehicle fire, what happens? Does it know how to safe itself so that it doesn't endanger the firefighters through unexpected motion? Just as an example. The infrastructure, the vehicle, the roads, the data networks, the cloud computing, road users such as pedestrian and light mobility users, emergency responders, and the environment, such as the operational design domain definition. The point is that everything that can possibly affect safety, that's safety related, has to be dealt with in the safety case, and there are sections on essentially all of that within 4600. As a further example, here are some operational design domain prompts. So this is a small subset of the types of things that are said to be important and that have to be included in a safety case for operational design domain. One is behavior rules, and it gives as examples traffic laws, vehicle path conflict resolution, local customs, justifiable rule breaking. There's also a compliance strategy of traffic rules and regulations. So the first one said you have to identify what the traffic laws are, but this one is how to argue that you actually conform to them and that you won't break traffic rules unless it's necessary or somehow appropriately safe to do so. There's a prompt element about vulnerable populations, including number, density, and types. There's one about special road users. And there's one about seasonal effects. Sure, it could be snowing, but Also, snow might be covering the vehicle even after it's done snowing, or maybe the leaves drop off the trees and that affects your localization ability, and so on. This is a small sample, but 4600 has a very robust list of the types of things you should be thinking about. Do you need technical mitigations for all of them? No, you don't. You need to argue in your safety case that if it applies to you, you have it covered somehow. And if it doesn't apply to you, well, that's okay too. Just say it doesn't apply and have a credible way of knowing that that's really true. 4600 also has a section on metrics. These are safety performance indicators, SPIs. They're sort of like KPIs, key performance indicators, but specific to safety. And what they do is they provide metrics on the validity of the safety case over the system lifecycle. As an example, if you have a pedestrian who's about to step on a road, you have to have some sort of safety metric that says how close you're allowed to pass to a pedestrian, and it's going to be context dependent, probably based on the area, the local customs, the speed of the vehicle, and so on. But at some point, there's such a thing as too close, and if you're too close, it's unsafe. So the SPI would say, for example, how often do you encroach upon a pedestrian closer than you really should for safety? SPIs differ from KPIs because KPIs are typically about average performance and whether your system is working well, whereas SPIs are about whether or not you're crossing a line that makes the system unsafe. Another type of SPI is based on assumption validity. For example, you may have a system that tolerates gaps of up to so many meters in lane markings. Now you may say in your ODD, in fact, that's true of all the lane markings. But when the day comes that a lane marking is obscured and that's not true, you need to know that that's been violated. So the SPI metric in this case is how often do your assertions about what the world looks like actually prove out to be incorrect. Hopefully not too often, but that's why you keep a SPI to check on that. Or, for example, you might assume that there's a certain very low false negative correlated rate between camera and LiDAR returns. Well, that's an assumption, and you won't really know if it's true unless you measure it over operational life and find out how it really turns out. So you want to SPI for that. 4600 also requires feedback loops, and the SPIs are a piece of this. That's how you make measurements for the feedback loop. The idea is, rather than assume perfection, because no matter how hard you try, systems aren't perfect, instead, recognize that these imperfections will be there, so you have to manage them and improve them over time to continuously improve the system performance, but also safety. That means feeding back the SPI data into the safety case and, over time, converting unknowns into knowns. As an example, you may find out that your system has trouble seeing children next to adults, that it misses them. And what you want is feedback loops so that when this happens and you realize, oh, we didn't see the kid, you fix it so you see the kid next time, and you do that before the kid actually has a chance to run into the street. The feedback loops are pervasive throughout the safety case. Basically, anything that's a value that you think is true that has to be true for safety, you need to be paying attention to, and you need to be feeding back data into the safety case to make sure it really is true. And that includes looking for implementation faults, design faults, gaps in the simulation, gaps in the operational design domain, and gaps in machine learning training data. 4600 also supports elements out of context. So think of these as components. It's similar in spirit to an ISO 26262 SEOC, but it is much broader in that it's hardware, it's software, it's sensor, it's map data. And it isn't quite about the component, rather it's about the safety case. So the idea is if you have a safety case for your entire system, what do you do about the safety case for the LiDAR or the radar or the real-time operating system? It may be the vendor does not want to expose the design details to the manufacturer, and so the manufacturer doesn't have a safety case, but they need to do something. So the EOC interface is a defined way that the vendor of a component, hardware, software, whatever it is, can say, all right, I'm going to do a safety case, I'm going to do independent assessment, I'm going to conform to 4600, and I'm going to produce an EOC interface that summarizes the things that are needed by the upper safety case. That includes the properties and characteristics of the component, the assumptions the system above must honor for the component safety case to be valid, the fault model used for assessment, and the coverage of the clauses, because it may or may not cover all the 4600 clauses, and an assessment report that sums all this up. So when you buy a chip or an operating system or a sensor, it should come with an EOC interface Then you plug the EOC interface in, and it replaces the stub of the argument that would otherwise correspond to that component. 4600 complements other standards. ISO 26262, MIL Standard 882, and so on are potential starting points. Those standards should be used where applicable, especially for functional safety. Other emerging standards can also be applicable. For example, ISO PAS 21448, having to do with SOTF analysis, and design and validation process frameworks, and SafeAd and emerging standards. All these sorts of things can and should be applied when applicable. But what's left out of those is the system-level approach for knowing that things are handled. As a simple example, 26262 will say do a hazard analysis, but it doesn't tell you what hazards you probably need to mitigate, whereas 4600 has extensive lists of did you think of that types of things. For example, in Pittsburgh, a sinkhole opened up and half swallowed a city bus. In this case, there was a human driver, and the human driver knew that even though the bus was not a bus stop, this would be a really good time to open the doors and let the passengers out. And those are the types of hazards that you might not think about unless they've happened to you. But 4600 gives you a way to learn from other people's experience and think of those sorts of things to decide if they require technical mitigation in your system. Here are some other key points. Self-certification is permitted. An internal assessor can be used. It has to be an independent assessor, but there's no requirement for an external assessor, assuming you have an internal independent capability to do assessment. Only necessary technical mitigations are required. You can argue does not apply to my system, or that's outside the operational design domain, and here's why we can say that. Those sorts of arguments are fine. So the ones that don't apply don't have to be used if they truly don't apply. Underwriters Laboratories is a nonprofit standards development organization. The voting committee, the STP, Standards Technical Panel, has diverse representation, including various stakeholders from government, from academia, from industry, and consumer advocates, and they are the ones who actually voted on and approved the standard. There's a continuous maintenance process in place to provide timely updates as well, so at least at first we expect that perhaps yearly the standard will be updated to keep up with the evolving technology. Does 4600 conflict with ISO 26262 or ISO PAS 21448? Definitely not. There were STP members who were tasked with ensuring that, and those STP members were actually on the drafting committees for those other standards. What if you can't afford to buy a copy? Standards can be quite expensive, especially for people who are just trying to take a look and see what's in them. Well, the good news is that UL standards are free to browse, all of them. So you can log on, you can get a free account, and you can see 4600 in its entirety in your web browser without paying anything. Let's recap some key ideas. The system-level safety case is required by 4600, and it provides direction for safety. It highlights gaps in evidence and arguments so that when you think something is true, you actually have a concrete reason to believe that, and you can point to it and say, yes, this is why it's true. The vehicle, infrastructure, and lifecycle processes all matter. If a safety case depends on it, that makes it safety related, and that includes not only the vehicle, but also data feeds, map data, infrastructure, and all the types of things that might be related to safety are covered by 4600. Metrics, SPI's safety performance indicators, are combined with feedback loops to make sure that anything your safety case depends upon being true for safety is actually looked at, and if it turns out to be invalid or things change over the life cycle, you'll get feedback to update your system and your safety case to maintain safety and improve it over time. There's a third-party EOC component interface that allows you to install third-party components without the third-party vendor having to reveal the details of their safety case. And ultimately, the point of 4600 is to help you know that you've done enough safety work. There are robust prompts and pitfalls that capture the best practices, lessons learned, so you can know, even though it's a minimum standard, you can know that you did a really good, thorough job of not missing anything obvious and learning lessons that were learned by other teams and eventually your team over time as you hopefully feedback lessons learned to further improve the standard.